first question in our 22-3 video lesson is, how do you calculate the energy that a battery supplies to a circuit? So if we look back on the escalator model of the battery lifts, has a chemical reaction to move these charges up into the positive terminal of the battery to give potential energy in that battery to add energy to this circuit. And so the way you calculate that is change in potential energy equals the charge times delta V. And then what happens is the resistor then, as the charge goes through the resistor, the resistor heats up and takes that energy out of the circuit. So the energy put in by the battery is equal to the energy taken out by the resistor or resistors. So we've learned in mechanics, and this is question number 2, what's the definition of electrical power? And we learned in mechanics that power equals work over time. It's the rate that work is accomplished. And we just also talked about that the work done by the battery equals that change in potential energy, Q delta V. So let's go ahead and we have power equals work over time. And we also then have power equals Q delta V over time. And if you notice, Q over T, we've learned that that equals current. So we now have this equation, power equals I delta V. You'll also see instead of delta V, you'll quite commonly see power equals I times V. So if we look at question number 3 that says, what is the equation for the power supplied by a battery? So we just found this equation, power equals current times voltage. But as you know, the battery a lot of times is called an EMF. So you can do P power equals I times the EMF. And if you look at a circuit, sometimes you'll see this power supply called EMF, sometimes you see it called V, so you'll see either one of these two equations. This is the resistor over here, and this is the current coming out of that power supply. So question number 4 goes on to say, what's the equation for the power used by a resistor? Well, we know that the power given by the power supply has to be equal to the power used by the resistor. In our situation here, if you have multiple resistors, they will just all the powers of each resistor add up to the power from the power supply from the battery. And we know that the current going through this resistor is I, and we also know that if we measure the voltage drop across this resistor, we'll get V, and so the equation is power equals I times V, just like the power for the battery, except this is the rate that power is being dissipated out of the resistor, instead of being given to the circuit by the power supply. Now, with Ohm's law, you can make this equation a variety of different equations. So let's say you take V equals I times R, which is Ohm's law, and you plug that in for V, and you get power equals I squared times R. Or you could take I equals V over R, which is another form of Ohm's law, plug that into the original power equals I times V, and you'll get the equation power equals V squared over R. So you'll see this power equation 3 different ways used in various problems, but it all means the exact same thing. You can derive one from the other. This example is a nice simple example. It says a car battery has an EMF of 12 volts. So we'll write that down here. When a car starter motor is running, the battery current is 320 amps. So we write that down here, 320 amps. What power does the battery supply? So that's simply power equals I times E, or I times V, whichever one. You just multiply those two numbers together, and you end up with 3,800. And the units here are volt amps, but power is usually measured in watts. So instead of volt amps, we would do watts. On the next page is 2213. It says how much current is drawn by a 75-watt light bulb connected to a 120-volt outlet. So we'll write down our given, and we want to solve for that current, so we just use the equation I equals P over V, which is the same thing as power equals I times V. And we just plug in our values, and we end up with 0.63. And it ended up being a watt per volt, which is actually the same thing as an amp. And lastly, we're going to do 22.14 at the bottom of the page. And it says how much power is dissipated by a 60 watt, 120 volt light bulb when operated using a dimmer switch at 100 volts. So what we're going to do here is look at what's going on at 120 volts, find out what the resistance of this switch is at 120 volts and 60 watts, and then apply that to the 100 volts. So we're going to use the power equation. Power equals V squared over R. We can rearrange that to be resistance equals V squared over power. So we're going to go ahead and plug in our 120 volts and square that. Our power is 60 watts. And this ends up giving us a resistance of 240 ohms. Now this resistance does not change. The resistor stays a resistor. The only thing that's changing here is the voltage. It's going to be 100 volts instead of 120, so then our power will be different as well. So we'll go ahead and use that equation, power equals V squared over R. But in this case here now, we're going to use 100 volts. We see that resistance stayed the same, 240 ohms. And so now we see that the power used on this dimmer switch at 100 volts is less. It's only 42 watts being used.